4.5 Signal distortion. There are two types of signal distortion. The first is clipping distortion. This is when an amplifier reaches saturation before we get the full signal out. So for an AC signal, it would look something like the following graph. If we applied this to a loudspeaker, the result would be harsh, as it would add high frequency components at the clipping points. They do expect you in the exam to put the original wave in a dotted line and the clip in as flat in a thick line. So how can we avoid clipping distortion? There are three ways of doing it. First is to increase the power supply voltage. This increases the saturation voltage and therefore means that hopefully we're not going to get clipping distortion. In the previous example, it was clipping at 12 volts and it wanted to go up to 16 volts, so we would need to raise the power supply above 16 volts. Bear in mind that 1 or 2 volts is usually lost, as op amps aren't ideal, so you're probably looking at maybe aiming for 18 volts or possibly going up to 20 volts to be on the safe side. The second way you can do it is to reduce the voltage gain of the amplifier by adjusting the resistors. Remember that V out is equal to the gain times V in, and the problem is V out is too big. So if we decrease the gain, then V out will go down as well. The third way is very similar, but this is to reduce the amplitude of the input signal. So either we can take the gain down to take V out down, or we can take the input voltage down. The second type of distortion is slew rate distortion. Remember, a slew rate is how quickly the op amp takes for a change in input to result in a change in output. It's given on the datasheet, change in voltage over change in time. Do make sure you've labelled it on your datasheet. Remember that this is the time it takes for the op amp to respond to an input change. So if our input changes from, say, 0 volts to 6 volts instantly, our output will take a little bit of time to respond. And if this gets too bad, so the change is too big and it can't respond, we end up with clipping distortion. Slew rate distortion, which is not good. What causes this? Inside an op amp, and do look it up if you have the time, because there's a lot going on inside an operational amplifier, it has capacitors. And if we end up with some stray capacitance, we may end up with some positive feedback, which causes oscillation before we get to the final value. There is one way of tackling that, and that is to add a capacitor to control the phase difference, something we'll look at more in year 2, but this will actually decrease the slew rate. Here are a couple of graphs to give you an idea. So this is for, the graph on the left is for a DC signal, where the dotted one is what we want to get, and the black one is what we actually get. And on the right, we've got an AC signal. Ideally, it should be a nice curve, a sine wave, but unfortunately, it takes time to respond, and we end up with this triangular wave, which is not good. So there is a requirement we need to make sure we avoid this. And this is that the slew rate is basically fast enough to respond. This is an equation that you are given on your datasheet, and it's 2 pi times the frequency. So we need it to be at least as big as the frequency of the input signal, times the peak voltage. Obviously, if there is a large change in voltage, if it's going from, say, 0 volts up to 20 volts, it will take longer for it to respond, so we may need a higher slew rate to account for that. Do make sure that you label this on your datasheet. And that is it. 2 different types. You need to know for clipping distortion the 3 ways of dealing with it. For slew rate distortion, you need to know this equation. Let's have a look at a couple of questions just to make sure that we understand. So on the right, we have got a non-inverting amplifier. You should be recognizing it, although they have actually told us in the question because they're being nice to us. And we're asked to calculate the voltage gain. Remember that gain is 1 plus RF over RI for a non-inverting amplifier. So that's 1 plus 39 over 1, which is 1 plus 39, which is 40. So it has a gain of 40. It asks us to calculate the bandwidth. Remember that the gain bandwidth product is the gain times the bandwidth. So we know that 40 times the bandwidth is this 1.2 megahertz. So the bandwidth will be 1.2 megahertz divided by the gain, which is 40. Dividing by 10 would give us 0.12 megahertz, or 120 kilohertz. Divided by 4 would give us 30. So 30 kilohertz is the bandwidth. Part C, calculate the 2 DC input voltages that just cause saturation. So this is looking at clipping distortion in effect. So we are told that it saturates at plus or minus 12 volts. So we know that V out is equal to the gain times V in. We know that it's going to saturate at 12 volts, plus or minus 12, and the gain was 40 times this input that will just cause saturation. So we do 12 divided by 40 plus or minus 12, because we're going to have 2 levels. So the input that causes saturation, 12 divided by 4 is 3, divided by 10 is 0.3, so plus or minus 0.3 volts. So that is the 2 values. Plus 0.3, if we go above that, we're definitely saturated. Minus 0.3, if we go below that, we'll also definitely be saturated. Do think about the characteristic graph. It's a helpful way to think about it. So that's the graph that looks like this. So what we're doing is calculating this value. We know that it's saturating at 12 volts, and that's at 0.3 volts. This is at minus 0.3 volts and minus 12 volts. Okay, last part, the time taken for the output to change from plus 3 to minus 3 volts. This is a change of 6 volts. And we are told in the question that the slew rate is 6 volts per microsecond. So it's just going to take 1 microsecond to change the 6 volts. Okay, question 2. And we're going through a few examples just to really make sure we've got those ideas nailed. So it asks us to estimate the slew rate. So we're not given it from a table this time. This time we are working it out from a graph. And we can see that it's gone up 10 volts in 3 microseconds. So the slew rate is the change in voltage over the change in time. So that's 10 over 3, 3.3 recurring volts per microsecond. Part B, calculate the maximum signal that will produce a distortion-free output for a sinusoidal output of amplitude plus or minus 10 volts. Well, we know that the slew rate, so this is the other equation we looked at with slew rate, to avoid distortion was 2 pi times f times the peak frequency, which is 10. So we just put this all in. So this is 3.3 recurring volts per microsecond. We might need to convert this to volts per second in a minute, because the frequency will be Or we can leave the frequency per microsecond. We just need to be careful. 2 pi, the peak is 10, and the frequency is f, which we are trying to find. So we do 3.3 recurring divided by 2 pi times 10, and this will be per microsecond, of course. So we will need to convert that into per second, because frequency is always written per second. So this is 0.05305, etc. Waves per microsecond. Now, to convert it to per second, we need to multiply by 1,000 to get it per millisecond, because there'll be 1,000 of these in every millisecond, and then times it by 1,000 again to get it per second, which gives us a final frequency of 53 kilohertz. Rounding, of course. Okay. If you are feeling particularly confident, of course, please do pause the video and have a go at these questions yourself. Question 3. So in this question, what have we got? We've got the peak voltage is 10. We can work out the time period. It's going to be 8 microseconds. That's the time for a complete wave. So we can put that all together. So the time period is 8 microseconds. So the frequency is 1 over 8 times 10 to the minus 6. So that is 125 kilohertz, because that's 1 over 8 microseconds. That's 125 kilohertz. So we've got the time period, we've got the peak voltage. We can put that into the equation. So that is 7.85 megavolts per second, or we could say 7.85 volts per microsecond. And that's just taking this factor of a million from the top, dividing both the top and the bottom by a factor of a million, which will give us 7.85 volts per microsecond. Okay, part B. The amplifier saturates at plus or minus 11 volts. Determine the maximum allowable voltage gain if the input signal with amplitudes in the range plus or minus 140 millivolts are to produce a distortion-free output. So this again comes back to V out equals gain times V in. We've got 11 volts, and we've got the gain, and that's got to be multiplied by up to 140 millivolts. That is volts. Let's make that a bit clearer. So the maximum allowed gain will be 11 over 140 millivolts. Watch out